Hello, you fine internet folks. I'm back home from SC, where I had an absolutely wonderful time, and I cannot wait for SC 25 next year in St. Louis. And while at SC, I had the absolute pleasure to interview Bill Starkey. Bill Starkey is the chief architect of IBM's Power CPUs. Now, some of you will know what IBM Power is, but some of you aren't. And this intro is more for you folks who don't know what IBM Power is. Now, IBM Power is one of two CPU lines that IBM makes. There's IBM Power and there's IBM Z. Now, IBM Z dates all the way back to the System 360 and is a very different lineage from the Power systems that Bill and I were talking about. Power, as some of you may know, was used by Apple for a long time in the Power PC series of MacBooks and Mac desktops. So for some of you, Power is a known quantity. However, for some of you, Power's been sort of out of the news as of late. There hasn't been a ton of talk about Power since the announcement of Power 10 at Hot Chips 2021. So historically, IBM has had an initial Power, so let's say Power 5, and then in between generations, so in between the Power 5 and the Power 6, they've had a Power 5 Plus, which is an incremental update on the prior generation of Power. And with Power 9, seemingly, IBM has dropped the Plus scheme, right? There was no Power 9 Plus. And with Power 10, that seems to also be the case. There doesn't seem to be a Power 10 Plus coming. Instead, what we're getting is the Power 11. And that is what Bill and I talk about, along with what the future for Power holds and what decisions they may make for future architecture. So, wasn't explicitly said, but Power 12. Anyway, I hope this little preamble before the video does clear up some things and why these questions were asked as they were. And it's largely because there hasn't been a ton of news of Power with regards to Power. So I was very curious about what was happening with it and what does the future look like for Power. So stay tuned, and here's my interview with Bill Starkey. Have a good one, y'all. Hello, you fine internet folks. We're still here at SC24, and instead of at the convention center, we're here at the Westin Peachtree with IBM. And I have with me Bill Starkey from Power, Chief Architect of the Power Division. Would you like to introduce yourself?
Hey, everybody. Good to talk to you. Yeah, I'm Bill Starkey. I'm the Chief Architect of our Power microprocessors, and happy to be here at SC24. It's been great. We had a little rain today, but a little soggy. But other than that, you having a good time? I'm having a great time.
It's been a lot of fun, a lot of good discussions, and a lot of filming, And I love your shirt, the Power 10 shirt.
The 10, baby. It's good.
So, speaking of Power, Power 10 was the first to have a logo of all the Powers, an independent logo. Are we going to see a Power 11 logo?
I would expect so. I'm a little less involved in designing that than I am the actual processor, but Power 11 is kind of right around the corner, shall we say.
Okay. And what is Power 11 going to look like in the sort of high level sense?
Okay, yeah, just sort of stepping back. If you've followed us over the years, Power 7, Power 8, Power 9, Power 10, we did a pretty big transformation going from Power 9 to Power 10. As we described it, we kind of tore the thing down from the core. We started up building a new one. With the focus, we're always, every generation, looking at where our clients are. We run enterprise. So I know a lot of people don't hear all the details about us. We're not super well known, but actually when you swipe something on your phone, when you click something, most of the time it's running through a power computer, hidden behind a curtain somewhere, running in, all the world's top enterprises. But so as we went to Power 10, one of the big things, if you recall the discussion then, we really focused on AI being infused into the enterprise. And even prior to that, we were playing a little more in the external accelerated AI. We were doing some really cool things with NVIDIA, which were really centered around big HPC and AI training. But once again, we're an enterprise business, so we kind of needed to make sure you could train models so that later on you can run them and inference them in your enterprise workflows. By the time we went to Power 10, we pivoted strongly back towards, let's focus on the inference now that we know that the world can do training properly. And that's been a huge area we've been venturing into. And I feel like with Power 10, we not only hit the workloads of the day and what we needed to get done, but we got the workloads of the future, much better addressed. So, sorry, that's a really long preamble to what are we doing with Power 11. What we found in the field is Power 10 has, even outpaced our expectations. Looking in the rearview mirror, it was exactly what we needed, and it's better future facing. So Power 11, we are not burning it all to the ground and starting with a lot of new DNA. We're actually going to kind of extend those capabilities, those architectural features that you see in Power 10, and we're going to augment them. And I can give a few examples, but I got to let you get a word in edgewise. You're the interviewer, but I can give some examples of that if you like.
So yeah, some examples. So the Power 11 core, is it derived off of the Power 10 core? And
yes,
what are the sort of biggest microarchitectural changes there?
Not a whole lot of change into the core itself.
Okay.
I mean, the Power 10 core knocked it out of the park. So yes, it's going to run faster. Yes, we're going to be able to enable, more cores. But fundamentally think of it as evolutionary from an architecture standpoint.
Okay.
And where we're really looking is, as we talk to our clients, what are capabilities beyond just those raw speeds and feeds that you need to get, or what are other aspects of the system where we can provide more value?
Yeah. So, but Power 11 is its own independent core. It's not. It's Power 10.
It's a new chip. Yeah.
Okay.
Yeah.
Cool. The reason why I asked that is because in some LLVM commits, it was Power 11 was essentially labeled as Power 10. So a lot of people had questions of, is it a new core or not?
So like in terms of any ISA changes, any new instructions, anything like that, no, the ISA is the same as Power 10 ISA. So kind of in the software-ish world, you're going to see like, hey, this looks the same. Well, yeah, you want to have continuity in your ISA. We didn't see any things where it's like, oh, we better add that new thing to it. I mean, and then when I said with Power 10, we feel like we addressed not only the present, but the future very well, that kind of goes hand in hand with that.
Okay. So I know that there was a roadmap a few days ago published, and the future Power chip looks a lot like AMD's Rome and Milan setup, where you have a single I/O die and then multiple chiplets.
Yes.
What drove you to that sort of design?
So we've been evaluating for many years, when is that time going to come with Moore's Law, where like, yep, we have to augment just doing new chips with packaging. And as you pointed out, we've seen that with our friends at AMD. We've seen that with our friends at Intel. We've seen that with our friends other places. People are evolving toward chiplet architectures to kind of overcome the physics limitations that Moore's Law, which was once our good friend, is not so much our friend anymore. So we need to do those things. So we determined for Power that the new thing we come out with after Power 11, I'm not going to say the name because we have to have official naming, but I'll let you guess the name of the thing after Power 11.
Maybe that's 12.
Well, I can neither confirm nor deny. But whatever that next thing is called, we are going to go to a chiplet architecture. And part of the reason we wanted to spell that out is we get that question all the time. I mean, it's, gee, when are you guys going to get there? What are the factors? Now, what's really cool, if you'd like, I can talk about some of what we've discovered as we evaluated these architectures.
Absolutely.
And you asked specifically, yeah, we look a little bit like the thing AMD did. AMD had to make trade-offs in what they did. Intel had to make trade-offs in what they did. It was interesting for me to see, because we kind of made the plan years ago. And as we saw, oh, here's what they're doing, here's what they're doing, we got to see the things that we conjectured for ourselves play out in the realities of what they're building. And we got to see, oh, how does this confirm or deny what our engineering analysis said it would? And basically, it's kind of matching our judgment. I mean, I don't know that I should make too many comments on what the competitors do. It's just my guesses. I don't want to say anything negative about anybody, but I would argue both AMD with their architecture and Intel with like Sapphire Rapids, they had to make certain trade-offs. I can see wisdom in what they both did, and they're very different, to address certain things, and I can see compromises they needed to make. And it just so happened that within the realm we play, which we're playing in a different world, we're playing in enterprise, and we're playing, especially we have our large system enterprise heritage. If you look at how those kinds of approaches might map, the thing we came up with just happens to look a little more like the thing AMD came up with.
Okay.
And I can go into more detail. I will say where I'm super excited is the areas I see they had to make compromises. That's some areas where we have some differentiation, where I feel like I'm getting the value of a chiplet architecture without having to make some of the negative compromises.
So, so what client workloads drove you to more of a IO with disaggregated compute, single IO with disaggregated compute, rather than, say, single unified compute and disaggregated IO?
So one aspect of that is just to build a large system. The worst thing you could do from a latency standpoint is do the compute at the center and disaggregated IO. Think of building a topology. It's not about building the socket. It's about building the connectivity across all sockets and internal to the socket. I like to call it the silicon radius. I need to engineer to the absolute lowest latency to get from one end of the silicon to the furthest end of the silicon in the system, not at a socket level. I also have to do that while I'm aggregating as much silicon as I can. So those are at odds with each other. So hence it's a fun engineering problem.
So we just saw the announcement from Azure and AMD about the MI300C chip. Now, what do you think of sort of, it looks like a mix of what Intel did with Sapphire Rapids and what AMD was doing. What do you think sort of that mix in terms of where you see things going?
So
do you see that as fewer compromises in terms of trade-offs? Because I know that a large trade-off that AMD had to make was you couldn't directly communicate between chiplets. Like you couldn't access cache you had separate cache.
Can we maybe suggest maybe they had to make some latency compromises and some bandwidth compromises?
Yeah, bandwidth.
Because of the kind of signaling, as opposed to if you looked at a Sapphire Rapids and all the small bump edge stuff, Intel, I believe, was saying we're going to build our full highway systems that run across this. And so I think what you're seeing is an evolution of AMD saying some of those, latency bandwidth compromises we made, we're going to make improvements to that. However, that leads to some of the compromises Intel made. So it's interesting. They're balancing somewhere between where they've been and where Intel is. And, the thing that, for us there, from our signaling technology that we use in our hub and, surrounded by compute model, the signaling technology is not requiring me to make bandwidth compromises. That's a twofold thing. One is just the capability of the kinds of on-package SerDes my engineering team is able to do. So as I map out the highways, I didn't get like, oh, we have to cut the lanes out. No, it's pretty much what I would have built on chip. But the other piece is because of our memory interface, we're not surrounding our hub chip with all these horribly inefficient DDR ports to talk to memory. We have our OMI memory architecture. That takes the signaling overhead for memory very low and enables us to put bandwidth in for other things. So it's a combination of really good quality signaling and the ability to get more of it in there. I don't have to make that compromise. It also helps me in latency, because the best thing you can do for latency is be outside of the silicon. The wires in the substrate run 10 to 50 times faster than in silicon wires. So the worst thing you can have is a big, big, big pile of silicon with, staying in the silicon. And latency, I think in my world probably matters more to me than any of these other folks, because I have to build really large 16 socket systems. I'm not trying to just build a single socket optimize or a couple sockets optimize. So it's different trade-offs that you're making for the different kinds of spaces. And so I don't mean to be, I'm not being critical of anybody. I'm just saying we have to do different things. And I really admire what both AMD and Intel have done with the constraints they have.
No, absolutely. It really was a question of what did you think of the blending? And I really liked your OMI, if you want to talk more about OMI, because that's a major differentiator for not just power, but also for any IBM system.
Yeah, our Z systems use OMI as well. And I mean, so there's another whole realm there. I just described the value of OMI in terms of it provides all this signaling, beachfront resource to do other high bandwidth signaling. That's one element. That's just because it is so beachfront area efficient, because you're essentially running a really high speed SerDes instead of running a really low speed DDR interface, relatively speaking. The pin counts are so much lower. But the other thing with OMI, well, there's multiple. I could talk forever here. I don't know how much time we have, but I'll hit the high points. Reliability, ultra reliability. One of the weakest components of any system is a DIMM connector. And running a DDR protocol over a DIMM connector, it's got to run, down through the module, through the motherboard, up over the DIMM connector, up onto the DIMM, hit the DRAM chips. As DRAM speeds are trying to go faster and faster and faster with these single-ended DDR protocols, I don't know how they're even going to do DDR6. I think the industry is kind of in for a nasty wake-up call here. I know they're dealing with it. I know people had a lot of trouble in this area with DDR5 signal integrity.
Yeah.
And so I don't have that. I'm not running a DDR protocol that way. I'm running this beautiful high-speed SerDes. If I have a problem, I do a replay. It's a really intelligent protocol, just like PCI. If you got to resend a packet, you take a CRC fail, you replay it. I also can steer around lanes. So if a lane goes bad or if there's something flaky in the DIMM connector, I can get around it, keep the system up and running. That matters for what we're doing in our Z systems, in our power systems, especially power, like our big SAP HANA workloads. You got tens of terabytes of memory that can never afford to go down. This is part of our secret sauce of how we get there. Now, the other thing, that's reliability. Also, because I'm able to run this so much more efficiently off the processor, I'm not stuck only putting like 8 DDR ports or maybe 12 behind a socket. I have 32 DDR5 ports behind my new memory architecture on a single socket.
So much higher bandwidth.
I can get to like 3-4x types of bandwidth, 3-4x types of capacities. Capacity is big too.
Yep, absolutely. Especially in the SAP HANA world where it's in-memory databases, and those databases can be 8, 16 terabytes size.
Or larger. We're certified much bigger than that, but yes, I think I'm going the right way.
Like in the past, we still have 8 socket systems, and it was almost specifically designed for SAP HANA work. So I guess moving forward, there is going to be power.
Oh,
power
definitely
exists.
So here's the other beauty. So we talked about Power 11. We talked about, and then beyond that, we moved to a chiplet architecture for that thing that comes next that might be named like Power 11 plus 1. But once you're on that chiplet architecture, the other thing we see is a path forward. We see, how to iterate within that architecture with the hub and the compute chips around. You can see how you can incrementally change things. You can see, first of all, allows you to get more silicon area in a socket. Well, and those are tiny little compute chiplets. You can see how those can grow as you need. You can see how you don't have to refresh the whole thing. So there is a growth path, and there's a set of development economics around that I will tell you, as a chief architect, I've been doing this for almost 30 years. Not as a chief architect, but an engineer working on the processors. I can see clearly further forward into the future than I ever have before. just because of, seeing, well, I could do this for the thing after, Power 11. I can do for the thing after that, I'll do this twist. For the thing after that, I'll do this twist. And I can see getting there in a much more economical way from a development standpoint.
Well, I guess I just have one final question for you.
Sure.
What's your favorite type of cheese?
I guess I love it. A Danish blue is really good with a nice glass of red wine.
Well, thank you so much for this excellent discussion. So we still have some more SC stuff coming out, hopefully, I think. Depends on when this video comes out. But hit that like button, hit the subscribe. I hate chilling it, but I have to. And have a good one, folks.
Hey, thanks so much for having me.
Oh, yeah.
I appreciate it.
Thank you so much. Thanks.
Thank you.